Hello students, a very warm welcome to JEE English by Unacademy, India's leading and largest test preparation and learning platform. Guys, is it streaming? So yes, hello students, a very warm welcome to JEE English by Unacademy, India's leading and largest test preparation and learning platform. And students, you are on JEE English, nation's first channel that delivers lectures for your JEE preparation exclusively and completely in English. And guys, we have the best in class faculty on this JEE English team who can take you from the basics until the depth of every topic that is required for your JEE preparation. And trust me guys, JEE is very easy if you take you from the fundamentals until the advanced concepts. And that is what we have been doing every day. Hi, hello, good evening to all. And today we are going to explore that, that awesome concept in this current and electricity, that is going to be about the measurement instruments. And let me tell you something, to know about this topic, you literally don't need any prerequisite. It's a very easy topic. Not only that, all you need to know is V is equal to IR. That's it. That's the only thing you need to know. But you typically get questions around this topic every year from on your JEE Mains paper and also many times on your JEE Advanced paper. It has a very good significance. You're using it in your labs and you have been often using it in your labs, but probably the working is the key. And for this, even today's lecture, we are going to discuss a lot on the working of this instruments, because that is the key. Even if you have noticed the JEE advanced questions earlier, it was just based on the working of these measuring instruments. Okay, let's get into the lecture. Let's not wait anymore. And people who know me well and good, else I'm going to introduce myself. I'm Muralidharan Gopalakrishnan. I completed my MS in Electrical Engineering from University of Colorado Boulder, and I'm an electrical engineer. And guys, I completed my BTech from IIT and I'm an IITian. I have 4+ years of experience preparing students for IIT JEE and other competitive exams. And I filed 22+ patent applications on this electrical engineering related topics in India, US and Canada. And students, today we are going to explore the current electricity. It's going to be awesome. It's going to be amazing. It's one of those most interesting topics if you ever come across, because there is nothing in it. You have to build from the the foundation and go through this topic, and it's a very easy topic. And we'll be also solving some JEE Advanced and JEE Mains problem in this session. Let's get into the topic. Let's not wait anymore. And before that, I would like to inform you that we have an awesome JEE_English channel on Telegram app. If you already have Telegram app, please do get onto this channel. It's an amazing channel where you can get all these updates on such sessions. And also we are going to do PYQ this coming Friday. Yes, of course. The question is, will this chapter be finished by the end of this week? Of course, we'll be finishing all the theoretical and the DPPs. We may have to do more DPPs on current electricity, but yes, most of the chapters will be finished by the end of this week. But anyway, and you can click onto this link to get onto a JEE English channel. The link is available in the description box below. And guys, if you don't have Telegram app yet, do install the Telegram app. Not only that, if you click on this link, you will get all this updates on our special classes, on our weekly progresses, etc. What we are doing this Friday. Like this Friday, we are going to discuss PYQs on current electricity, and you don't want to miss it out. And this session is something you don't want to really miss out. And guys, not only that, if you have Telegram app, you can also get onto my personal educator channel, and you can type in Murali at the rate of Unacademy to connect with me, and we can you can share all your doubts, etc. queries on this channel, or else you can just type in https://t.me/Murali_Unacad. And students, this Friday and Sunday, we are going to have an awesome special class where we are going to discuss current and electricity. And these two lecture sessions will be probably covering the entire current and electricity as we were covering until now. But the thing is, it's going to be only an A to Z lecture, so we'll be missing out some of the model problems. But anyway, it would be a great concept revision for many of you. It's from 4 to 7 p.m. It's a free special class. Do not miss it out. It's from Unacademy and Unacademy JEE English. And students, how to attend such special classes? You may want to download the Unacademy learning app, and you can get this app on Google Play Store or the App Store. Guys, do get on to this app, because we have many such special classes going on this Unacademy learning app, and it's altogether a very different experience. You get all this timely notifications on all of our like classes that are being conducted over there from various educators. So do not miss it out. And students, if you're preparing for IIT JEE and if you're looking for an awesome platform for your JEE preparation with live quizzes, etc. and etc., this is the platform, guys. Like we have all this live quizzes, live test series. You can get interaction sessions with your educators of your preference. Not only that, you can also get doubt clearing sessions with them. You have leaderboards, you come to know your standing. So what are you waiting for? You may want to purchase the subscription. And you know what, the subscription is not also very expensive, it's very economical. It's a very economical package with all these benefits, with 6,000 plus materials, and it hardly costs 1,500 per month if you're going for like a 24-month subscription, which is very reasonable compared to any of the packages. And guys, you can apply a Murali Live coupon to get a 10% instant discount on this purchase. And if you're 9th, 10th or 11th class, you may want to definitely choose the 24-month subscription because it's 2-year or more long journey. So be sure to get this 2-year long subscription. And guys, do not forget to click the subscribe button, bell notification, and like on this video. And this lecture is going to be awesome. It's a JEE English channel. It's a free of cost channel for all your JEE lectures in a single place. And guys, today we are going to have an awesome quote from Feynman, one of the renowned scientists. So he said that I don't have any answer. If I do not have any answer, don't get frightened by it. But he's enticed by losing into this mysterious world with any purpose. I mean, within any purpose means here it's with any purpose, which is with the way really it should be. So far I can tell, and it does not frighten me. So what he means to say is like he's never frightened about not knowing things. He rather enjoys this journey of exploring this mysterious universe. And you are doing the same thing. You are come to this lecture, or you are attending all this physics lectures. You know very well that everything is not known to you from the beginning. You have started now. Many of you may have started now. Many of you already have the this conceptual built up from your earlier classes. But anyway, you should not ever get frightened by not knowing answers to what you're coming across. You should be rather enjoying it. You should be rather exploring it. You should be rather trying to crack all the problems in your JEE exams. And be it your test series, be it anything, to take it serious so that you are going to enjoy it. And today's topic is going to be awesome and amazing, and it's going to be a very short lecture compared to rest of the lectures because it's about electrical instrumentation. And guys, the most important thing is try to get the concepts right away. You should not be even going through another like a PDF or something, or any other document to understand it. It should be like within this lecture you should understand everything. And let me tell you, if you understand the basic things around this measuring instruments, it's going to be super easy and super awesome. So let's get into the topic. Let's not wait anymore and get into the topic. And it's going to be an awesome lecture, and you don't need any prerequisite, and it's really easy. You'll notice that the JEE advanced problems were also very easy. So guys, let's get started with the galvanometer. Galvanometer was first invented in 1800s and odd. It's a revolution in electrical measurements. Okay, so first electrical measurement, I mean in terms of this electrical currents and everything, was done using a galvanometer. Back in the days, people think about it. Back in the days, people didn't know how to do things. What is this current, etc., etc., etc. But now we know everything. So it does not seem like an obvious thing. I mean, not an obvious thing. It seems like an obvious thing that you put this probes across. But this construction of galvanometer is so important because it lays the foundation to rest of the electrical measurement instruments in this lecture, or in anything that we are going to discuss about electrical measurements. And guys, so when we are talking about galvanometer, so what is a galvanometer? Galvanometer is nothing but a moving coil placed between these magnets. So if you are noticing, this is one specific kind of galvanometer. Okay, this is not the galvanometer. We are going to probably study the moving coil galvanometer. Okay, the moving coil galvanometer, the coil is moving everywhere. In each and every galvanometer, the coil is moving, and this is a sort of galvanometer where you have like a horseshoe magnet. This is a horseshoe magnet. It has a south pole and it has a north pole. If you notice this, and if you see, there is a spring. Okay, there's a spring over here. So if you're watching this like this animation and simulation, you're seeing there's a pointer. So this pointer is acting according to the current flowing in the coil, and these magnets are maintaining the magnetic field. Okay, so there would be a deflection when this current is flowing in, because there is going to be a change in the magnetic field once the current starts flowing into the coil. And the springs over here, the springs that is being shown over here, is taking care of this entire, counterbalancing action. We'll understand that. I mean, like, you don't have to worry if you're not getting anything right now, because it's an amazing topic. And in this case, there is a mirror is not typically required in a galvanometer. It depends like on which kind of galvanometer you're dealing with. So basically, you need a magnet. You need, like a DC magnet, I mean like a permanent magnet or something like that, and you need a spring. Okay, and you also need, like a coil, definitely a coil. And the coil over here is over here, if you have noticed on this, green kind of thing. And this coil is where the entire game begins, and this coil keeps rotating, this pointer will also keep rotating. Okay, so the moving coil, two magnets, and a spring. And there is a dial, of course, which has been calibrated accordingly to measure the currents. Let's get into the topic. Let's not wait anymore. So this was the first kind of galvanometer that was invented in 1800s and odd. If you notice, it's the same thing. If you notice, this is the, like the pointer. There is no difference. This is the pointer, and this is the scale. Back in the days, this was like the scale. We not have, like digital scales. And this is like the horseshoe magnet. This thing, this this black color thing is the horseshoe magnet. And if you notice this, there will be some current flowing inside this coil. There is this coil over here, right? There is this coil over here, and in this way this galvanometer works. And galvanometer is actually a revolution in electrical measurements. This is how everything began. And so this is like the typical, like an sort of a thing to better understand what does a galvanometer have. So if you are noticing, there is, like a scale that we have just seen, and there are like like a north pole and the south pole magnet. There is a north pole and the south pole of the magnet, and typically this current that will be flowing inside this, like this golden color thing. This golden color thing is the coil through which the current will be flowing, and based on that, this pointer will be rotating along with this. Pointer will be rotating along with the coil. Okay, this pointer is rotating due to the coil. Because the coil is, why is the coil rotating? Because there is change in current. There is a new current flowing inside this coil, which means this new current is going to, del cross, E is equal to is equal to E. Del cross B is equal to E, or del cross E is equal to B. So, like, due to this flow in the magnetic, like the electric current, a sudden flow in the electric current, there is going to be a magnetic field, and this magnetic field is going to enable this rotation of the coil. Okay, this coil will be rotating. So try to understand in 3D itself, it would be very easy. So there would be a spring which would be counterbalancing everything. And actually galvanometer is not just an electrical instrument, it's an electromechanical. Rather, I like to call it magneto-electromechanical or electromagnetical mechanical. So it's also used as an actuator. So it's like, sometimes used as an actuator. It's not a motor, exactly not a motor. So in this you have like, a limited range around which this, like the pointer moves. The pointer moves within certain range, and that is very important for this. Like why galvanometer? Like why not, like why not we can use galvanometer for every application? You start understanding it. It's not a motor. It's basically like, it can be used as an actuator. In some cases it has been used as an actuator. Like you can, yeah, like, the principle is pretty much the same. So now what happens over here is, we like think about it as the first instrument that has been invented for measuring currents. Okay, the speciality of, like the galvanometer is like, it can detect currents. Like it can detect currents, very very small currents, like microampere currents. So these kind of current can be detected using galvanometer, not, very easily using an ammeter. Ammeter typically has, like a larger like current range, but at the same time it measures larger current. Okay, but nothing, will understand it like what is ammeter as well in this lecture. And guys, so the basic thing in galvanometer is going to be like your permanent magnets, and this is a moving coil galvanometer. We're not talking about, like the tangential galvanometer that would have a very different working principle as well. Not a very different working principle, but in that case you would be taking, instead of theta, as tan theta. Okay, and that being said, this is going to be like the coil, this, coil within which the current would be flowing. And there would be a spring. Okay, there would be a spring, and this, these are the main things. These are the main things that is enabling the working. So to make it work, to make it look like working, what would you do? You would attach a pointer, and there would be a scale. You would calibrate the scale. Okay, that's it. Okay, now what is a galvanometer? A galvanometer is nothing but an electromechanical instrument used for measuring or detecting very small currents. And galvanometer is very sensitive. Like it can detect small currents. At the same time, if you pass a large current through it, the galvanometer would get damaged. Okay, a typical galvanometer of the older times would get damaged if you had passed a very large current through a galvanometer. So do remember, galvanometer is an electromechanical instrument. It's not just like an electromagnetic instrument. It's an electromagneto-mechanical or an electromechanical instrument. Okay, there is a mechanical action that is also going on in this galvanometer, and the pointer on the scale tries to indicate the flow of the current, sometimes the direction of the flow of the current. In few galvanometers it will start from zero, and there will be the like you call this deflection. Okay, the movement of the pointer is known as deflection, and the deflection can be sometimes on the both sides. In some galvanometers you typically start from zero and it goes until some point. And how do you measure this magnitude of this small current? So this current that is flowing inside this coil will be measured using the calibration of this this pointer. That's it. And the deflection of pointer is due to, why is the deflection happening? It's due to the electromagnetic torque. You are having an electromagnetic torque, and which is being counteracted by a spring. Okay, the spring that you're seeing over here. Okay, which restores basically the deflection. That's it. So the instrument has to come back again to the zero once the current has passed it. So that would be taken care by the spring. Spring acts like that restoring device for this galvanometer. And what is happening, like in this galvanometer, the sudden this currents moving inside the coil produces a magnetic flux, and this change in the magnetic fields gives a torque to this current carrying coil. So the coil should start rotating once the current comes in. So it's very critical to understand, or it's very crucial to understand, that this coil is going to rotate. Okay, rotating coil, do remember that. And the coil rotates due to electromagnetic force, or you can call it like electromagnetic angular force or torque, and the pointer thus attached will also move, and the mechanical spring is basically trying to restore the position of the coil. It produces a counteracting mechanical torque. And this is a very important concept, students. This is a very important concept. The next thing I'm going to talk is very important concept. In fact, it was asked in your JEE Advanced. So carefully be attentive, and also call your friends onto this lecture. They would also love to learn about physics, current electricity, especially about today's lecture, which you are seeing pretty much every day in your lab. So in galvanometer, something that we haven't talked about until now, but you have been noticing that the unique thing in this picture. So in galvanometer, there is something known as a soft iron core or a ferromagnetic thing that is placed between the coils. So if you notice, there is this coil. I'll mark it with maybe another color. So there is this coil, and this coil that I'm marking right now is surrounded by inside the coil there is a soft cylinder, soft iron cylinder. Soft, I mean, is not soft in terms of hardness, mechanical hardness, but in terms of ferromagnetic hardness. Okay, so it's a soft iron core thing, and it is placed inside this coil. So it should be very sensitive, right? The entire objective of galvanometer is to be very sensitive. Then what would you have to do? You would have to enhance the magnetic fields inside the the coils, and also inside that area. So this is taken care by this soft iron core. You need to understand this really critically, because this is a very important concept, and the soft iron core is taking care of enhancing the magnetic fields, and also it makes that this magnetic fields are flowing in radial direction. Okay, the magnetic fields are in radial direction. Why is it happening? Due to the soft iron core. Do remember this point. What are the things present in it? One is there is a permanent magnet, and guys, this is a cross-sectional view. Okay, this is a cross-sectional view. You need to understand this. This is a cross-sectional view. So what is happening inside this? There is a spring which is restoring, which is attached to a moving coil. I mean, it is sort of this coil is moving. Think about the spring like a circular spring. The circular spring is trying to pull back the movement of the pointer. And what is happening is this coil is rotating on its own as soon as there is a current inside it due to the varying, like the electrical field, which is having this, like another magnetic force is being produced. And this magnetic force with this, like this, due to this presence of this, permanent magnet, there should be torque. Okay, there should be a torque. And once this torque comes into the play, what is happening? There's a magnetic field that is being produced. Now this magnetic field has to be uniform. It has to be uniform, it has to be more enhanced. That is when this torque is going to be more efficient. That is being taken care by that soft iron core. And these things are like obvious to you now. I guess there is a scale, there is a pointer. Okay, so it's basically a coil, right? Think about it. It's basically a coil-based device. A coil-based device which has a soft iron core. You are basically placing the soft iron core to enhance the magnetic fields and as well as to influence the direction. It should be in radial direction. You are influencing this field direction using the soft iron core. And these permanent magnets are present over here because they are necessary for this torque to happen. And there would be a spring to bring it back to the normal position. Okay, the initial position. So now let's get into the, like the mathematical part of this, like galvanometer, how to work around the equations around galvanometer. So when we're talking about, like galvanometer, we are concerned about torque. So there are two kinds of torque. One is the restoring torque due to the spring. I can write this as K into theta, where K is going to be, like the spring constant, or you can also call it, like torque per, like, or couple per, couple per twist. So K is nothing but either it's a spring constant or couple per twist. Both are like the names given to it. Like in some people to call it as, couple. It's basically couples per twist. Okay. Hi Vinu, hi Vinuvardhan. So stay attentive in this class, students. This class you might not get many doubts, but a very easy to score topic where you don't have to put any efforts. All the efforts that you have to put is in this class and during your test series. That's it. That is all you need to do. It's a very easy class, and do call your friends onto this lecture as well. You don't want to miss this lecture. It's an amazing lecture. It's very practical. So this K is typically denoted as couples per twist. Okay, or it can be also, in general term we call it as spring constant, right? So we are going to derive something very important. Just to remember that, like what we are going to derive. I hope you understood. This is spring constant, this is couples per twist. It's the same thing. So I'm saying this torque over here, the mechanical restoring force is going to act due to the spring that is present in this, like galvanometer. And what would be that? That would be like K into theta, depending on the angle of deflection. More the angle of deflection, more would be the mechanical spring torque. Okay, and more deflection is happening means there was, like a large current flowing through this, like galvanometer coil. The coil is this one over here. Do remember, this is the coil. Okay, and what is this tau? This tau is nothing but NIA into B. What is N? Number of turns. Number of turns of that coil. Okay, number of turns of that coil. More the turns means more the torque for the same amount of current. And I means current, you know that very well. I is current, I'm not denoting I. A is area, B is magnetic field. I hope rest of them are fine. N is nothing but number of turns of the coil. You see that coil over there, right? There is a coil, and that coil, that the golden color coil, if you twist it more and more, you will get more torque. Okay, there is this coil. If you have more number of turns, means more electromagnetic torque. Okay, and there would be more the current, means current we are not controlling it. Current is flowing through a circuit. We can control area. Okay, and as well as the the magnetic field. But anyway, now you need to understand that what we are going to do is we are going to balance the equation at an equilibrium position. So this is going to be like present as soon as the current is flowing in. There would be like an immediate deflection in galvanometer. It's very sensitive. There is going to be an immediate like deflection in the galvanometer, and you are going to balance it at some point. It's going to be equal to K into theta, where K is the spring constant or couples per twist. So basically now I can write this equation as just basically what I'm doing over here is, if you notice it, what is happening over here, I'm basically writing it I is equal to Basically writing down this equation in terms of I is equal to something into theta. That is what I'm trying to do. Like I is equal to some k by NAB into theta. The theta is called as deflection. The terminology is deflection. So the key is the terminologies in this chapter, students. Okay, it's logical. It's the most important things over here are the terminologies. Try to understand the terminologies right away. Do not delay anything on understanding the terminologies. So K is known as couples per twist. So they will give you in the question as like K couples, this many couples per twist, and they'll say this many divisions or this much angle or something like that. Okay, this much deflection has been there or something. This they will say it as couples per twist. Okay, or like spring constant or something like that. And this would be like like deflection is the typical term. It can be also tangential coil. We are not going to discuss tangential coil. We are primarily going to discuss moving coil, which is the most like the significant topic in your JEE. And now think about those days when there weren't like electrical instruments. So how are you thinking when there weren't electrical instruments? You are typically thinking in terms of mechanical, mechanical things. Degrees is well evolved, deflection is well evolved. Okay, but current is not yet well evolved. It's 1800. Still people are thinking about currents. Currents is still a new thing to them. So what I did is like I tried to write current in terms of like theta, and I'm calling this K by NAB as 1 by S. And what is this 1 by S, students? This 1 by S is 1 by sensitivity. More appropriately said, it is current sensitivity. Okay, this is a key concept. Current sensitivity is what? A material, I mean like the like instrument property, right? Current sensitivity is an instrument property. What all it is dependent upon? Number of turns, area, magnetic field, and the couples per twist or the spring constant. Okay. Okay. Now that being said, now what am I doing is I have this equation where I know like current is 1 by S into theta. Okay, they'll just talk about sensitivity. Do remember that in your questions they'll just talk about sensitivity. You need to understand sensitivity is nothing but if just blandly said as sensitivity, or if it is plainly stated as sensitivity, that means we are talking about current sensitivity. Okay, now I can also write theta deflection angle or deflection is equal to, so it's basically deflection. You don't want to write this as deflection angle, it depends on the type of galvanometer you're dealing with. Deflection is equal to S into I. So now think about it. Back in the days, they were thinking, like mechanical, measurements were the standards. So you're trying to correlate. In fact, even in today's measurement instruments, you are correlating this mechanical scale, right? The scale, that measurement scale you have is still, like digital scales have come up. That's a different thing. But like think about the analog scales. They are calibrated based on some inches or like centimeters. So they're trying to think about mechanical deflection in terms of like current. And how do you correlate them? Theta is equal to S into I, where S is the current sensitivity or sensitivity. This is very important, students. This is very crucial. Okay, and now I can write this. S is nothing but, let's say there is some unit deflection. There is a small deflection for some small current. I can state that S is nothing but that small deflection per small current. So they may give you an like an equation like some in terms of theta and I. Okay, you might have to differentiate. They will say this theta of that spring or like whatever it is, like the system is something like I square T or something like that, I square A B C D, something like that, plus of something. Now what would you do if they ask you to find out current sensitivity? You'd basically take d of theta by d of I. Okay, and then you would get the sensitivity, value of sensitivity, current sensitivity. Okay, it is unit deflection per unit current, which is nothing but NAB by K, isn't it, students? Okay, awesome. Now let's understand the symbol of galvanometer. A galvanometer is typically like shown in this way. There would be a G and this would be the circle. Like basically for any, if you remember, any measuring instrument would be stated something like this. So in terms of when you're talking about galvanometer, it would be shown something like this, or it can also be sometimes indicated like this. Either of them is the way to show galvanometer. Now talking about galvanometer, so there is a small current that is flowing inside galvanometer, Galvanometer is not a very ideal thing. It has a resistance. Okay, an ideal galvanometer should have resistance 0. And basically V is equal to IR equation, right? V is equal to IG into RG. So the voltage drop across galvanometer is nothing but IG into RG. But in this case, as I told you, galvanometer has a like a limitation. The limitation is this IG can only go until certain limit. There is a certain limit for this full deflection current. That is what we call it as full deflection current. So there is a certain limit for the current that can flow inside galvanometer. There is a certain limit for the current that can flow inside galvanometer. More than this current may typically damage your galvanometer. And this maximum current which will give like full scale deflection. Let's say now the pointer comes over here, and this full scale deflection, when it happens, there is certain current flowing in it. This is called full scale deflection. Maximum deflection on the like the scale. Okay, this is called as full scale deflection, and for that there would be also a corresponding current. Okay, resistance is constant. Resistance is like the galvanometer's like property. So this full scale deflection is dependent upon a full scale current. Okay, this equation holds true for like any current and any sort of thing, because R then that the voltage that would be produced across galvanometer. But in this equation we are specifically talking about full scale voltage and full scale current. Okay, this is called full scale current. Full scale means full deflection has happened, full scale. Beyond that the deflection cannot happen, or beyond that the current cannot flow. Beyond that, if the current flows, your instrument may get damaged. And similarly, this is called as full scale voltage. Okay, this is called as full scale voltage. That's it. That is the most important thing. And you understood that this deflection and current can be related. That is, deflection is equal to like sensitivity into current. I'll check it out, your video problem. We'll get into this chapter. Stay attentive in this chapter. It's a very easy chapter, but as well as you will get many questions in this. JEE Mains, typically you get a question. 1 or 2 questions you get in JEE Mains. Okay. So now, guys, I'm guessing no one will have doubt in this chapter as we move along. Probably somewhere, maybe once we come to maybe like challenge questions, we'll be doing, like many challenge questions, many JEE based questions in this chapter. Okay, I'll talk to the team. Maybe you can get in touch with the customer care about your device not showing it. Okay, not YouTube. I don't know. I'll talk to the team. Okay. Now coming to this full scale. Okay, this is full scale deflection. You are understood that full scale deflection current is nothing but current required for complete deflection. So let's say my galvanometer has this galvanometer over here as maybe like this many number of divisions. If you see on this yellow scale, there are certain number of divisions. I'm saying there are like 60 divisions. Okay, 60 divisions. Yes, please do comment on the comment box below if your device is not working, if I'm not audible, because I checked the videos today, I was audible. So do try to get in touch with the team. Maybe you can comment on the video, or maybe also you can get in touch with maybe Unacademy customer care. So that way there are like 60 divisions. So this 60 divisions is what we are calling as deflection. If there are 60 divisions, there are total number of divisions would be 60 divisions. Okay, total number of divisions would be 60 divisions. The last division would be 60th division, and the current required to create that 60th, to move this pointer until that 60th division is called full scale current. Okay, current required to move the pointer to that 60th division, where we are talking 60 divisions has the maximum divisions. To move it to the maximum division is called full scale current. And we can either denote this internal resistance or the resistance of galvanometer as G or RG. So in your problems, they will directly give you G, or they may give you RG. Anything may be given, and typically they will use IG. IG is current flowing into galvanometer, not necessarily the the full scale current, but generally it is full scale current. Okay, generally it is full scale current, and the resistance of galvanometer is generally in the range of 10 ohms, or 1 ohm to 1 kilo ohm, 1 or 10 kilo ohm. It's a high resistance, I guess, but yeah, it's generally like this. And there is a beauty of this resistance. If you make use of this resistance, you'll understand how to even make other instruments. And IG, this current that will be flowing through the galvanometer will be in the range of microampere to milliampere, not more than that. If you are going to flow ampere current through it, you are probably damaging galvanometer. They may ask you a question. Okay, let's say the full scale deflection current of galvanometer is 10 milliampere. I've suddenly passed 10 ampere through the galvanometer by mistake. Something happened, my circuit was shorted somewhere, I didn't notice it. So now what would happen to your galvanometer? Or they would ask something like that, I am trying to again measure that points, and what would I notice? Would I notice any current, or would I not notice any current? I will not notice any current, right? The instrument is already damaged. It's a very important concept, you need to understand this point. Okay, and similarly, I'm going to define something, a new quantity called as voltage sensitivity. Okay, we heard about current sensitivity. When we are plainly speaking about sensitivity, means it is current sensitivity, and it also can be voltage sensitivity. Here I'm indicating with U, maybe any term can be used. So when I'm relating deflection, this deflection on this scale with some sort of current, then I'm calling it as some current sensitivity. Like on the scale, if I'm trying to denote the current, then I'm saying that current sensitivity into current is nothing but deflection. Similarly, I'm saying over here, the deflection is nothing but U is nothing but over here current sensitivity. Okay, U is current sensitivity, voltage sensitivity. I'm really very sorry. This is voltage sensitivity. Okay, this is voltage sensitivity. Same thing is written over here. Okay, so U is voltage sensitivity. Now I can also say that deflection is nothing but just calibrating things. Think about calibrating things. Same thing can be calibrated, right? Instead of a current, I can also make use of voltage sensitivity to calibrate the number of voltages or the amount of voltages across a terminal or something. So I'm doing the same thing. Now I'm defining a parameter known as voltage sensitivity, and I'm multiplying it with the the number of volts, and finding out in terms of deflection. And these two equations can be equated, and from there you will get that if I'm equating equation number 1 and equation number 2, and I will get that voltage sensitivity is nothing but current sensitivity. S is current sensitivity into current. Okay, this is current sensitivity or sensitivity. Okay, current sensitivity or sensitivity into current divided by voltage, or the potential difference. Okay, V is nothing but potential difference. So that is going to be S divided by RG. What was RG or G? If you remember, the resistance of the galvanometer. So this tells you the relationship between voltage sensitivity and current sensitivity. Maybe they will ask you in terms of voltage sensitivity. Okay, so it's S by G, and this is also nothing but deflection per unit voltage or unit volt is called as the same thing, same kind of definition, but in terms of voltage. There it was deflection per unit current, here deflection per unit volt, and that is nothing but S by G, where S is current sensitivity and G is the resistance of the galvanometer. So it's again going to be NABK by G, if you remember all these terms. Okay, now guys, this is like a standard voltmeter. It looks something like this, but all the voltmeters may not look something like this. Now we are also understanding that galvanometer can also tell you about the direction of the current. If the current is flowing this way, or if the current is flowing this way, some galvanometers would be able to tell that thing as well. Okay, this is how the scale of galvanometer looks. So what is the full scale deflection over here? 30. Agreed? 0 is over here, and there is minus 30. So the full scale deflection of this galvanometer is something like 30 divisions. Okay, and the current that will be flowing to reach this 30 divisions is called what? Full scale current. That's it. You can find it out using this, and also you can find out full scale voltage. Easy. Now let's get into the concept challenge problem number 1. Students, get started on this. Until now you understood all the concepts, how a galvanometer works. Now you need to get started on the answer. Anyone who has just even begun with the class will be able to answer this thing, given that you understood the concept. Okay. Now tell me, like, which of the following is, like, in a given galvanometer, the sensitivity of the galvanometer can be increased by, let's say I have a galvanometer, I want to increase its sensitivity. Sensitivity means current sensitivity. Then what would I do? Or even, you can take voltage sensitivity in this case. Should I increase the number of, can I increase the number of coil turns by increasing what? By increasing the number of coil turns, will I get more sensitivity? Amazing, amazing, yeah. Will I get more sensitivity by increasing, spring constant or couples per twist? No, I won't. If you remember, what was sensitivity? NAB by K. If you increase the spring constant, that means what is going to happen? Think about it. More rigid the spring, less the sensitivity, less this, that pointer can move in the galvanometer. So that spring constant is going to hamper the sensitivity of your galvanometer. So you do not want, a material that has, like very high spring constant or couples per twist. Of course, length and breadth of the coil. Why? More the length, more the area. More the breadth, more the area. Okay, easy question. Amazing, students. You already understood the concept, I guess. And now what about this? In a given galvanometer, the sensitivity can be reduced by decreasing the strength of magnetic field, or by choosing a spring with larger spring constant or more spring constant or couple per twist, or by decreasing the coil area, or by decreasing the scale count. Which of the following are true, students? How do you reduce the sensitivity of the galvanometer? So if I decrease the strength of the field, my galvanometer may not be precise in terms of torque. Yes, it's going to be A, B, C. So if you decrease the strength of the current, D, scale count is irrelevant. I'll come to that point. By decreasing the strength of the current, the strength of the magnetic field, you will reduce the sensitivity. By increasing the spring constant, it will become more rigid. That means you will decrease the sensitivity. So this is also correct. This is also correct. By decreasing the coil area, also you will be producing lesser torque. I will conduct a Menti quiz. Okay. By decreasing the coil area, you'll also reduce the sensitivity. Okay. Lesser will be the torque. Lesser will be the torque. Lesser will be the torque. Scale count does not matter, right? Scale count is you are developing it. It is not related to sensitivity. Awesome, amazing. Now let's do a thing. Using these concepts itself, we will get into an IIT JEE advanced problem. Get started on it, students. Get started on it. I want answers from everyone. It's an IIT JEE question. In fact, I discussed this concept. Okay, I discussed this concept. Try to get it. What is happening? So it's like the question is saying, it's a JEE advanced question, guys. 4 marks question for nothing. If you understood the concept, it's 4 marks in your pocket, or in your, like whatever you call it. The sensitivity of a moving coil galvanometer is increased by placing a suitable magnetic material as core inside the coil. If you remember the moving coil, you are placing a core inside the coil. Why are you doing it? Is it true that, sensitivity of the coil of the galvanometer is increased by placing a suitable magnetic material as the core inside? And the reason is, they are stating that the reason is the soft iron has high magnetic permeability and cannot be, easily magnetized or demagnetized. Amazing, amazing, yes. So see, it is true that, your assertion is correct, isn't it? Your assertion is correct. Your assertion says that the sensitivity, to increase that sensitivity, you are placing that magnetic material, so that your fields are enhanced, you get the radial direction and everything works accordingly. Yes. And is it true that if you are the soft iron core has high magnetic permeability and cannot be easily magnetized or demagnetized. No, it can be easily magnetized and demagnetized, right? It can be easily magnetized and demagnetized. That's why you are placing that soft iron core. So this is false, right? This entire, this thing is false. It cannot be easily magnetized or demagnetized is false. It can be easily magnetized and demagnetized. So it's going to be C. It's a JEE advanced problem. You'll also keep noticing the JEE advanced problem are going to be easy in this chapter. Now come to this. This is like not really like a conceptual. It's like a conceptual question only. You can just do it orally without putting in much efforts. A galvanometer has a scale with 200 equal divisions and has a current sensitivity of 20 divisions per microampere and voltage sensitivity of 1 millivolt per 2 divisions. Okay, 1 millivolt per 2 divisions and 20 divisions per microampere. Is there any difference between them? What is the internal resistance of the galvanometer? What should be the answer? See, it's like all those problems that you used to do in a 9th or 10th class, or not in a 9th or 10th class, like 4th, 5th, 6th class. That's it. That is all you have to think about. Basic things that you need to think to work around these kind of problems. So, like your 20 divisions are giving you 1 microampere. Agreed? Yes. Let's check it out. Okay, and 2 divisions are giving you 1 millivolt. What are you going to apply? V is equal to IR. That's it. V is equal to IR. You want to find out R. So R is going to be V by I. What is V? 1 millivolt. And what is going to be I? And you need to balance out for the number of divisions. So for 20 divisions it was like 1 microampere. Now for 2 divisions, what it is going to be? 2 divisions is giving you 1 millivolt, and 2 divisions of this is going to give you how much? How many microamperes? 1 by 10 microamperes. Okay, it's going to 10 kilo ohms, right? Did you understand this point? It's going to be 10. Okay. V is equal to IR, 10 into the power minus 3. It should be 10. Okay, that's correct. Yeah. It's going to be 10 to the power minus 6. It's going to 10 to the power 10 by 10 to the power 10, like 10 plus 3. That is going to be 10 kilo ohms. C should be the answer. If you didn't get it, let's do the problem again. Let's understand it this way. So now there are total, like 200 divisions. Okay, but this way is not very friendly. Let me tell you at the beginning itself. It's going to take a lot of time. 200 divisions for a full scale, like you're going to calculate like for full scale. What is full scale current? Full scale current is going to be how much? For 20 divisions you have, for 10 divisions you have 1 milliampere, sorry. For 20 divisions you have 1 microampere. For 200 divisions you will have 10 microampere. And similarly full scale voltage is going to be, for 2 divisions you have 1 millivolt. For 200 divisions you are going to have 100 millivolt. Again you are going to do R, or like in this case it is G is equal to V by Ig. This is 10 to the power minus 6. That's going to be 10 into 10 to the power 3. That's going to be 10 kilo ohms. Or else you can directly say from there itself, you can calculate for 20 divisions and go about it. 20 divisions is giving you 1 microampere. That also means 2 divisions is giving you 1 millivolt, means you also know like 20 divisions are going to give you like 10 millivolt. Easy. So from there also you can conclude that it is going to be 10 kilo ohms. Okay. Now let's get into next question. Yeah, that's correct answer, right? Now, what about this? A galvanometer as a scale with 100 equal divisions. Now, let's not, get into all the calculations. Just try to do it right away, just like this. So, a galvanometer has a scale with 100 equal divisions and has a current sensitivity of 1 milliampere for 10 divisions. And if they gave you unequal divisions, that means what are you going to do? You are going to calculate for the full scale sensitivity to calculate the resistance of the galvanometer. Okay. And the voltage sensitivity of 1 millivolt per 2 divisions. Same thing. Yes, that's going to be like, yeah, 1 millivolt per 2 divisions. So it's going to be 5 divided by, yeah, it's going to be 5 ohms. That's it. Basically, I hope everyone understood this problem. It's going to be like, 1 milliampere for 10 divisions. For 10 divisions, you will have 5 millivolt. 5 millivolt is giving you, like 1 milliampere means it is 5 ohms. Okay. Now let's get into the next question. A galvanometer of resistance. Now this is an interesting one. Okay. Little bit you need to put down the pen to calculate this question. Okay. Maybe if you calculate just like that, well and good. A galvanometer of resistance 50 ohm is connected to a battery of 3 volt along with the resistance of 2950 ohms in series. A full scale deflection of 30 divisions is obtained in the galvanometer. In order to reduce the deflection to 20 divisions, the resistance of in series should be. You have a galvanometer, it has some resistance of 50 ohms. You have initially connected to like a 3 volt battery and also in series with 2950 ohms. A full scale division of 30 divisions is obtained in the galvanometer. In order to reduce it to 20 divisions, what should be the resistance? Okay. So how do you do this? It's a basic problem, right? Current is nothing but what is current? Current is going to be K into theta or K into deflection. So for 30 deflections, you had how much current? 3 volt. Okay, 3 volt divided by the total resistance 2950 and 50. Okay, is equal to how much? Sorry, K, it's not K, it's C, it's S. I'm really very sorry. Okay, sensitivity, right? Let K as any constant, okay, just a constant into theta. S into 30. No, the question is asking you what is the new resistance that should be placed in. What is the new resistance that should be placed in, series to get it down to 20 divisions? Get it down to 20 divisions. So you need to find the value of resistor. Read the question carefully. You can maybe go back a little bit and read the question and come back. Okay. So where were we? Now this is going to be 30. Okay, this was earlier, right? Now you wanted to bring it down to 20 divisions as your new standard thing, full scale division, full scale deflection. In that case, you just know one thing, that is 50 is the thing that you know. What is this is that you don't know. Some X you are placing in series. You're placing this in series, so you don't know that X yet. So S into 20. Basically, you need to equate S or substitute that value of S. You'll do the same thing, and once you do that, I would rather equate the value of S, but it is traditionally better to substitute the value of current. I mean the value of S in this equation. But if I'm going to equate it, what am I going to get? 3 by 3000. Yeah, 3 by 3000. So divided by 30. Don't go for the full calculation ever, in questions like this. So you will have some sort of, there will be like a hint around the calculation. It will basically come out as, like something like 4500 minus 50. If you notice it, it is nothing but 4500 minus 50. 1 by 20. So 3 will get cancelled. And you will take this 20 on the, rather you won't take the 20 on the top, you'll bring this thing over here. And you can already cancel out the 0, 0. It will be like, like this would be like 1500. That is going to be 4500. X plus 50 is equal to 4500. That means the value of x should be 4450, which is going to be option D. Yes, that is going to be option D. So be careful while working around these kind of problems, because where it goes wrong is like you may also maybe influence to mark 4.5 kiloohms. But you need to carefully notice that the answer is like this thing. Sorry, not this thing. Sorry, not this thing, but this thing. D. 4.45 kiloohms. Okay, 4.45 kiloohms. Now let's get into the next question. A galvanometer with 100 divisions has a resistance of 10 ohms and a current of 10 milliamperes gives you a full scale division. Then what is the current sensitivity? Guys, come on, nothing to do in this. What is the option straight away? Without thinking anything. Something does not have any relevance in this question. What is that thing? This is not a lot relevant to a calculation, right? 10 ohms. So it should be how much? Yes, no. B, yes, sorry. I'm noticing it wrong. Okay, I'm thinking this is the B. Yeah, it's B. Yeah, 100 divisions divided by 10. That is going to be 10, right? So 10 division per milliampere. Do notice the units as well. Okay, that's it. So now let's get into the next question. Similar one. Okay, and then it's voltage sensitivities. Now they are asking you about the voltage sensitivity. Same problem. There are 100 divisions, and this 100 divisions have like a current of 10 milliampere gives you a full scale division. Now find out the voltage sensitivity. How do you find out the voltage sensitivity? Voltage sensitivity, what would you do? You can either do d theta by dV. You can either do d theta 100 deflections by dV, which is nothing going to be 100 by 100. Yeah, option is C. How are you going to do this problem, guys? It should be an easy one, right? There is nothing in this. So voltage sensitivity, if you remember, I took it as U. It's d theta or theta by dV. How much is theta over here? 100 divisions. What about number of volts? Yeah. See, 10 into 10. You have 10 ohms and a full scale current is 10 milliamperes. So it's going to be 1 division per millivolt. That's it. So this chapter actually does not have a lot, but we'll get into it. Now get into this concept problem number 3. So it's a concept challenge problem, guys. Now try to crack this question. A galvanometer can be used to measure direction of the current depending on the type of galvanometer. Very large currents, very small currents. Put in a circuit combination, it can also measure large currents and large voltages. Which of the following is true? What can galvanometer measure? Galvanometer can measure only small currents and its direction, and as well as also sometimes also small voltages. Okay, small currents, no, actually voltage itself, not small voltage necessarily. Yes, direction of the current depending on the type of galvanometer, it can only measure like small currents, not very large currents. Remember, large currents will spoil your galvanometer. And put in a circuit combination. No, put in a circuit combination. Now I haven't introduced you to that concept yet. Put in a circuit combination it can measure large currents and large voltages. Okay, this is also correct. This is also correct. Yeah, I'll speak a little loudly, but I guess maybe you must try increasing your volume or something like that. Okay, am I audible now? So put in a circuit combination, a galvanometer can also measure large currents and large voltages. This is where we are going to get into the concept of ammeter and voltmeter. First we'll understand the ammeter. So what is ammeter? Ammeter is nothing but like an instrument to measure large currents. So this was typically the first kind of ammeter that we had around. Okay, ammeter was like invented in 19th century, like 1800 and 1890 and odd or something like that. So this is the first kind of ammeter. If you see that ammeter itself used to measure like back in the days anywhere around 20 or like 2 something amperes. So ammeter is denoted by something like this, A inside, whereas galvanometer had G inside. Okay, and ammeter is typically placed in series with the circuit. If I want to measure the current on this resistor, okay, what is the current on this resistor is something that I want to find out. Then in that case, what would I do? I would attach this ammeter in series. If I am attaching only in series, I can find out the current on this component, right? If not, I can't find out the current on the component. So ammeter is an instrument that can be used to measure large currents. So how would you measure large currents? Now think about it, like a galvanometer can be converted into an ammeter. Basically, ammeter is nothing but a coil with something new. I'll introduce it, something new to you. But ammeter is used for measuring large currents, and do remember, ammeter must be placed in series where you want to measure the current. Okay, this you must already know, I'm guessing, and I placed it in series with this resistor to measure the current. Okay, ammeter looks something like this, but not exactly, it wouldn't deflect, keep on deflecting like this. Okay, so now if you have a galvanometer, this is a galvanometer, right? There's nothing else but a galvanometer, isn't it? This is just a galvanometer. You place a shunt resistance in parallel, then it is nothing but an ammeter. Okay, this is a very important concept. This is where most of your problems will appear around. Most of your like numerical problems will be around ammeter, mostly around ammeter. Else they're asking you what is the reading of ammeter given a resistance of ammeter. An ideal ammeter does not have any resistance. An ideal galvanometer does not have any resistance. An ideal voltmeter does not have any resistance. But whereas an ammeter has a resistance. Do understand that point. Okay, what you will do is, this shunt resistance, galvanometer will be spoiled if large current passes through it. But now you are trying to measure large current using the same galvanometer. How can you do that? You can place a small shunt resistance in parallel to the galvanometer to make it happen. Okay, you can place a small shunt resistance in parallel to the galvanometer. Small, very tiny. Okay, in parallel to the coil, or it can be galvanometer, anything, to make it happen. And you typically call this process as shunting. Shunt resistor, shunting, shunt resistance, a very small resistance. This maximizes the, why do you do that shunting process of shunt resistance? One is to measure more current, because most of the current will flow inside your RS. You already know the resistance of galvanometer. Okay, you know the resistance of galvanometer, right? You already know the resistance of galvanometer. Now if you place the shunt resistance in parallel, the current in parallel combination would get divided according to 1 by R, right? In parallel, the current ratio is going to be 1 by R, isn't it, students? So in a parallel, the current ratio would be in ratio of 1 by R. So this is in parallel, right? So 1 by Ig this to 1 by Is is going to be like Rg I'm calling it, or it can be just G is to Rs. Same thing. Just take an inverse. Okay. Now that is the key concept. So the key concept is saying that now you can let more current pass through shunt resistance, and little current will pass through the galvanometer. A little current will pass through galvanometer, and using that current you can sort of intuit the total current in the circuit. You can intuit or you can calculate the total current in the circuit using this little current in the galvanometer. But whereas you have originally this current is actually large. And how you did it? You used a very small resistance shunt resistor. Okay, small resistance. So what happened? Most of the current chose this, like the small resistance part. And what also happened? You are able to measure a large current, and you are protecting the galvanometer as well. Easy. Now this how it typically looks like. Instead of Is, I can write it as like I minus Ig. If the total current is I can call this thing as I minus Ig. Shunt current. Shunt current is nothing but the current flowing through the shunt resistor. Okay. Can I say this, students? The voltage drop across the shunt resistor and the voltage drop across the galvanometer should be the same, because they are in parallel, right? They are in parallel with each other. So the voltage drop is going to be the same. I can write I minus Ig into shunt resistance is equal to Ig into G. Okay. Now this is like, I would recommend not remembering the entire thing. Okay, if you want to remember, this equation is going to be super complicated. Maybe not for some of you. For some of you it's going to be super complicated. So what you can do is you can remember this part of it. In parallel resistances, the voltage drop across shunt resistor and the galvanometer should be equal, and among those the current is dividing in terms of galvanometer's current and the current of galvanometer subtracted from the original current. That is I minus Ig into S is equal to Ig into G. Okay, the same thing is written in this form, where S is the shunt resistance. So in your questions they will typically talk about shunt resistance. If they are talking about shunt resistance, probably resistance placed in parallel with a coil or with a galvanometer. And you also want to make sure that S by G ratio is as small as possible. The ratio itself is very small. That means this device does not have any resistance. You are placing it in the parallel. There should not, in series. I'm really very sorry. You are placing ammeter in series. In that case, there should not be any potential dropping across that ammeter. How do you make sure that happens? S by G should be very small as possible. And let me tell you an interesting fact, students. I want to ask you a question over here. Okay. To produce an ideal ammeter, can I make the shunt resistance as 0? Can you think about it and tell me? Maybe you'll get this question very soon in some of your exams, or maybe not. But can you make shunt resistance is equal to 0 for ideal ammeter? Is it something that you can do? Exactly, no, that's correct. It cannot be 0. Why? If it is 0, no current, no deflection would appear on your galvanometer. There would be no deflection. Many of your books state that like S can be 0. But if your S is 0, no deflection will happen. Your ammeter would not work. How much ever current will pass through it, your ammeter will not, the current will not flow through your like galvanometer, and there would be no deflection. Okay, there would be no deflection. Okay, S cannot be equal to 0. It can be very low, very small, so that you can measure large currents, but it cannot be 0. If it is 0, then galvanometer will show no deflection, because all the current will pass through this part of the circuit, and there will be no current, no deflection. So it's a good concept. Let's get into the next thing. So get started on this problem. Now most of your problems are going to be around shunt resistance only. Okay, shunt resistance is where you'll get most of your problems. So deflection in a galvanometer falls from 50 divisions to 20 divisions when a 12 ohm shunt resistance is applied. Actually, amazing students. I'm really, like quite, like surprised and perplexed that yeah, amazing, students on this channel. And do share this channel on all possible social media. Do, help people reach about this channel, because it's a free of cost channel where we are delivering, like very high quality lectures for your JEE preparation. So do not forget to do that, and guys, do it, Broccoli, do it, Abhishek, do it, everyone. Please do share the channel, Sabrish, on your social media. Do not forget to do that. We want more students on this channel, more brilliant students like you on this channel. So a deflection in a galvanometer falls from 50 divisions to 20 divisions when 12 ohm shunt is applied. See, that is what is told to you. 12 ohm shunt is applied means 12 ohm shunt is applied in parallel. Okay. 12 ohm shunt is applied in parallel. It was 50 divisions initially, now it fell down to 20 divisions when you have put in a 12 ohm shunt in parallel to create an ammeter. Just think about it, you are trying to create an ammeter. Then the resistance of the galvanometer is, it's a simple, sort of problem. Amazing students. Yeah. What did you say? No, think carefully, think carefully, think carefully. Okay, let's get started on it then. Okay, this is red. I'm going to choose like a yellow. Let's start with a yellow color. So 50 divisions was your initial current. Okay, 50 divisions was giving you an initial current. Okay, students, that is going to be sensitivity into 50 is equal to something Ig. Okay, this is the total current. Initial current is nothing but the total current that was flowing through it. Now you attached at a 20, right? 20 or 12. 12 ohm in parallel to this galvanometer. What has happened? Some current will flow through this and some current will flow through here. Now the measurement from 50 fell down to 20. Okay, measurement from 50 fell down to 20. So now let's understand this problem. So it fell down to 20 means, can I say that, now through, if it fell down to 20 means 30 of the current out. So total current had to be, this has to be the total current. Now can I say that 30s? So anyway, if 20, now after shunting with this 12 ohm resistor, you are getting 20 deflection. That means through G, Sn to 20 is passing, whereas through this new 12 ohms, there should be Sn to 30 going through it. No worries, Suraj, get started on this topic. It's a very easy topic, scoring topic, and you get a lot of questions in your mains. So you understood this concept, right? Now 20 is passing through it. I'm just directly multiplying that Sn to 20. Sn to 20 is going to be your current through galvanometer, and through the 12 ohms it is going to be Sn to 30. Remaining 30 has gone somewhere, right? 50 minus 20 is nothing but 50 minus 20. Okay, understood? Now what you need to do, that voltage, equating the voltage thing, voltage drop across this 12 ohm resistor and galvanometer is the same. Okay, voltage drop across 12 ohm and galvanometer should be same V. This V, this is also V. So what would you do? You basically write it down as S into 30. Yes, you probably took it as 20, I guess. S into 30 pass through 12 ohms. And how much pass through, galvanometer? 20. We already know it's 20 divisions. New divisions are 20 divisions, whereas initially it was 50 divisions. Basically S is nothing but telling you the amount of current, right? So you can equate it. How much it is going to be, 18. I'm not going to do the entire thing. It's going to be this is going to be 6, this is going to be 3, it will remain intact. It's going to be 18 ohms. Okay, you got this point. So it is 18 ohms. Simple, really simple. Okay, don't make any mistakes in this problem. This chapter you should be very clear, both conceptual and this kind of problems, because it does not take any time. If you are moving along in this chapter, maybe next chapter will be like little bit time consuming, but this chapter is not going to take any time. And if you move along with me and complete everything in time, like it's a cakewalk. And you need to understand galvanometer concepts to get into even potentiometer. Okay, potentiometer requires galvanometer concept, not necessarily ammeter concept, but you understood, right? Ammeter is placed in series to measure current, voltmeter is placed in, I'll come to that. Okay, and galvanometer measures small currents, and ammeter is measuring larger current. You shunt a galvanometer to find out that larger currents, because most of the current, if you put a very small resistance, small shunt resistance in parallel to a galvanometer, most of the current will flow through it. And galvanometer, what all it does have, it has a permanent magnet which is creating that field. It has that permanent field around there, it's as a magnetic field. Then there is a coil that can move around, and there is a spring which is creating the torsional, or the torque. And once this current moves into this coil, there is a rotation, there is a torque. And what is placed inside that, between that coil or inside the coil, there is a soft iron core. Why is it placed? It's placed so that the magnetic field can be enhanced, and also you can give a radial direction. Okay, these are the key concepts. So a galvanometer coil has a resistance of 15 ohms and gives you a full scale deflection of 4 milliampere. To convert it into an ammeter with a range of 0 to 6 ampere, how much resistance should you connect in parallel? So how are you going to do this, students? Are you going to go through the entire process, or are you going to adopt a easier one? Amazing. Do notice your points. See, are you sure? See, 15 ohms. Any day more than 4 milliampere cannot flow through galvanometer. Okay, this is G into Ig. And how much this ammeter has to measure? Something like 6 amp. So remaining 6 amp minus 0.0004 milliampere. So I can say 6 amp minus 4 into 10 to the power minus 3 into the shunt resistance is equal to G into Ig, which is nothing but 6 minus 0.4. Can I just say hi Alas, hi. 6 minus 4 into 10 to the power minus 3, it's going to be 6. I'm just assuming it's just 6 into RS. I'm ignoring this part of it. This is 15 into 4 is 60. It's going to be 10. If you bring the 6 over here, this is going to be 10. Okay, that is going to be 10 into 10 to the power minus 3 ohms. That is going to be 10 milli ohms. C. Okay. Hi Alaz Mansuri. Do call your friends onto our channel. It's an amazing free of cost channel where we are delivering quality lectures, and do not forget to share this video and channel. And student, this is a very easy chapter. Do stay attentive throughout the chapter, and you can easily score your JEE Mains. So you got this point, right? What did I do? I basically equated the shunt resistance, the current through shunt resistor, which is nothing but 6 minus 6 minus 4 milliampere into shunt resistance. That is what I did, right? 6 minus 4 into 10 to the power minus 3 into RS is equal to G into Ig. How are you getting it? Like it is 15, right? Do it again. G into Ig. What is G given to you as? 15 ohms. Okay, what is Ig? Maximum current that can flow through this, galvanometer resistance. 4 milliampere. Beyond 4 milliampere, it cannot measure. It will get damaged. Okay, or it can't show on the scale. Okay, so it's 15 into 4 into 10 to the power minus 3. is equal to the rest in the 6, it has to measure 6 amperes. 6 minus that 4 milliampere is going to flow through shunt resistance, this 10. Okay, 6 into 10 to the power minus 3 is going to flow through the shunt resistance into shunt resistor, right? How much is this? I'm just taking away this because it's not so significant. It's not so huge, and you need to do this in your exams. So this is how much? 16 to 10 to the power minus 3. 15 by, like 4. 15 into 4, I mean. Sorry, 15 by 4, not. It's 15 into 4. 60 into 10 to the power minus 3 divided by 6. That's going to be 10, right? 10 milliohm. Okay. 10 into 10 to the power minus 3. How did you get 10 into 10 to the power minus 3? How are you directly equating 10? It should be 10 milliohm. Check it out again. It should be 10 milliohm. Okay. Let's get into the next problem. So basically, what did I do? I basically equated 15 into 4 milliampere is equal to 6 minus 4 milliampere into some resistance. Okay, it should be 10 milliohms. The deflection of a moving coil galvanometer is nothing but galvanometer that we have discussed. It's reduced to half. Deflection in the moving coil is reduced to half when you are placing, like you're shunting it with a 50, ohm coil. Okay. Then the resistance of the galvanometer. So you are attaching another coil in parallel. Shunting means you are attaching another coil in the parallel. Now the deflection has become half. What should be, come on students, you should right away answer this. What should be that shunting resistance, or what should be the resistance of galvanometer? What is the resistance of galvanometer? You check it out. I'll get into it later. I mean, I'm sure that it should be 10 milliohms, but you can check it out. Maybe I'll check it out as well later. But now, what is the thing? Half of the deflection is only happening. Half of the deflection is only happening means, yes, exactly. Half of the deflection is only happening. If any other value, you would have to calculate it a little bit. If only half deflection is happening means half of the current is only flowing through it. Okay, half of the current is only flowing through it means in parallel it should have been equal to the 50 ohms of the shunting resistance. So answer is D. Okay, now let's get into the concept of voltmeter. Voltmeter is rather very simple compared to ammeter. In ammeter, you had to place a shunting resistance, very small resistance in parallel. But whereas in voltmeter, what you would do is you'd place a heavy resistance, a large resistance series. And what is a voltmeter called? A voltmeter is denoted with something like this V symbol, you know it. Ammeter denoted with A, not I. A. Voltmeter denoted with V. And voltmeter is used to measure the electrical potential difference. And this is one of this old kind of voltmeter which used to measure 10 volts. One of the first kind of voltmeter. And if you notice, there is nothing but, like a small, like I'll just, highlight it with the yellow. So that's more visible. See, there is a small, like a galvanometer, right? This is like a galvanometer. What is it? It's a galvanometer. Which is a red. There's a galvanometer over here. Okay, this is one of the oldest kind of voltmeter. Voltmeter can measure like large voltages across it. You measure any kind of, between any 2 points, you'll try to measure the electrical potential difference. That is what voltmeter does. And voltmeter, how do you place it? Ammeter, you'll place it in the series. Whereas voltmeter in a circuit, you will place it in parallel. Okay, students? Voltmeter, you will place it in parallel. This is voltmeter. If you want to measure the voltage drop across this resistor, you will connect these 2 points. There can be also another resistor. You need not worry about it. If there's a load resistor, there might be also internal resistance. You can also assume there is another resistance. But to find out the voltage drop across this load resistance, You're going to place voltmeter in parallel. And what is voltmeter doing? Voltmeter is basically measuring this, this potential difference across these 2 points, right? It's measuring potential difference across these 2 points, these two terminals, or these 2 points, these two terminals, anything you like to call it. Okay, voltmeter is an instrument for measuring, the voltage or potential difference across, two terminals or 2 points in a circuit, or across an element like load resistance or something like that. And it is connected in parallel where you want to measure the voltage. You can't connect in series. If you connect in series, it will measure its own volt, not any external volt, okay, or volt of any other circuit. Okay, easy. Now let's get into the concept of voltmeter. How do you prepare voltmeter from a galvanometer? You place a very, very large resistance in series. Very large means very large. It should be very large than galvanometer. And now think about it, when I'm placing large resistance in series, even small current can create a huge deflection in galvanometer. And when I am placing, voltmeter is going to be connected in parallel, right? Voltmeter is going to be connected in parallel. So if I am placing a very large resistance, like infinite resistance, okay, placing infinite resistance in parallel, see, again it cannot be ideally infinite, but you can call it as like infinite. It's fine if you get it in a question and they ask you infinite resistance can be placed in parallel. Yes, you can say that, yes. Because in that case, still galvanometer is going to work. Some small current will flow in. If like very infinite, maybe not. Okay. Like an open circuit, no, it cannot be an open circuit. You cannot compare a voltmeter with open circuit. It's not an open circuit. If an open circuit current won't flow, you won't find the deflection. So if you place it in parallel and if you have very large resistance, very large resistance, then what would happen? Majority of the current will flow through that circuit element only, which is what you want. You don't want all the current through, flow through this external measuring equipment or the external measuring instrument that you are using. You want all the current through to flow between these terminals, but through the instrument, not over here. Here very small current should come, else your galvanometer is at risk and your measurement is also going wrong. So you want small current over here, okay, and this should be very large for that to happen. Do remember that. That's it. That is what is voltmeter. Very simple. A small Ig will flow, and that using that you will be calibrating it for voltmeter. So that way, if you are placing large resistance, you are also protecting the galvanometer because much current can't flow through it. Okay, and the equation is going to be rather simple. This is like how you would think about a voltmeter. I mean a galvanometer or a coil with a large resistance, and you can say this: the same current is going to flow through R and G. Okay, so it's Ig is equal to IR is equal to I, and both are in series. So you will add the resistance of galvanometer and you add the resistance of like your voltmeter and multiply it with full scale deflection current or any current that is flowing through galvanometer. You'd get an equation like this, but don't remember this equation. All you need to remember is this thing: V is equal to R plus G into Ig. If you're very good in remembering formulas, yes, you can go for it. And R over here is the resistance of the voltmeter. Okay, you want R as large as possible to create the best voltmeter. Let's get into the question, students. The full scale deflection of the galvanometer is 2 milliampere. To convert this into an ideal, so it's an ideal galvanometer. Okay, this ideal galvanometer to a voltmeter with a range 0 to 100 volt, how much resistance should be connected to it? Come on, students, just get started on this. It's very easy. Yes, Abhishek, I know it's the easiest chapter. Among even electrical measurements, galvanometer is the easiest chapter. You need to understand some, like just the basic concepts. In fact, you saw like a JEE advanced problem was there. It was a conceptual problem. Even the next JEE advanced problem we'll be seeing will be a conceptual problem. Not a conceptual, I guess a little bit of numeric should be done, but that is all it is. So now come to this question. A full scale deflection of the galvanometer is 2 milliampere. To convert this into an ideal galvanometer, this ideal galvanometer means this galvanometer does not have any resistance. To a voltmeter of range 0 to 100 volts, how much resistance should be connected to it? No answers until now? Okay, I guess. So you should get 100 volt. So basically V is equal to IR. That's it. V is equal to IR is what you would apply to get the answer. Okay. Hi Vinith, hi. So V is equal to IR means 100 volt and the current is 2 milliampere only, right? 2 into 10 to the power minus 3 into the resistance of your voltmeter. So your voltmeter resistance should be, this should be 50 kilo ohms. Yes, it's T. Should be 50 kilo ohms. That is it. There's nothing in this. Voltmeter, you're not probably going to get any question, don't worry. Okay, now this kind of question is something that you can expect. Okay, there are 8 identical cells, so this kind of questions will come up. You know, where they have given you a voltmeter, maybe they give you a resistance of the voltmeter, they give you a resistance of the ammeter, and they'll ask you questions. We'll do that questions in the coming DPPs, but first we'll try to cover the syllabus and understand the basic concepts. Okay, yes, it's 50 kilo ohms. Yeah. So 8 identical cells marked 1 to 8, each having EMF 50 and internal resistance 50 ohms are connected as shown in the circuit diagram. What is the reading of the ideal voltmeter? The ideal voltmeter means infinite resistance and no current is passed. I mean, you are not going to take a parallel combination of it. So now how do you do this? What should be the answer? We have done this problem before, right? Even if you apply, you typically go for a Kirchhoff law. You write down all this resistances, all this volts, but think about it. You are going to measure V minus IR, and here all the cells are in the same direction, or they are cancelling it out each other. This also cancelling it out. If you apply Kirchhoff law, this also cancelling it out. Yes, it's 0. Apply Kirchhoff law. How much current is flowing through the circuit? How much current is flowing through the circuit if you are applying Kirchhoff law? The potential is all cancelled out. This will cancel out 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 this finally. So it should be 0. Because there would be no current in the voltmeter. It won't measure the EMF. Okay. This is the terminal voltage that it would measure. And so no current, that's why 0. Else it had to measure the EMF, right? So 0. Awesome guys, let's get into an IIT JEE advanced problem, and this problem, guys, start answering it, students. It's an easy problem. Think about the simple ways how we solve the problem until now. You'll be able to do this JEE advanced problem within like few seconds. Few minutes, let's say few minutes. Maybe like few seconds it should be. A moving coil galvanometer of resistance 100 ohm. Number 8 and 4 do not cancel out. Yes, actually number 8 and 4 do not cancel out. That's true. Yeah. So there should be an answer across the voltmeter. Yes. Actually this 4 should have been on the other side. It was basically a conceptual question. So then you'd apply Kirchhoff law and calculate, like the current, and then you would come to still know that there would be in that case a voltage. There would be a voltage, but my objective of bringing this question was I wanted to keep it like this and this, so that you get a 0 volt. The reason was why I wanted to tell you that this is going to be 0 volt if it is going to be like this. That is true, Suraj. Yes. This is going to be 0 volts is you are measuring 0 volts not because of EMF but because of no current flowing into the galvanometer. Okay. It would not be 50, I guess. It would be like, there would be 2 additions of voltages, that is going to be 100 volts. 100 volts divided by 400. 100 volts divided by 400 is going to be something like 0.25 amperes. 0.25 amperes into 50 is going to be like I guess 12.5 volts. So 50 minus 12.5 volts, that's going to be 37.5 if you're going to measure across it. But we don't have that option, but the entire gist of the question was to intentionally keep it in the opposite direction so that you understand that since you should not go for the EMF as the answer. You should not go for this as the answer if given a question like this. Else you go by Kirchhoff law and you will get the answer as 37.5 volts, because 8 resistances in series, 8 resistances are not cancelling out, only the voltages are cancelling out. Okay, there would be like terminal voltage across each and every battery if you measure, okay, due to their internal resistances. Okay, this and this only will cancel out in the original problem. Okay, if I'm moving around the loop like this and this would cancel. And that way it will be like only 250 volts would be additive. 8 and 4 would be additive, means it's 100 volts, but there are 8 internal resistances. 100 by 400, that's going to be 0.25 amperes. 0.25 amperes into this internal resistance across this battery only. If current is flowing, there would be a minus of internal resistance. So minus of internal resistance is going to be 50 minus 50 into 0.25. Okay, that's going to be 50 minus 12.5, 37.5. Okay, but you understood the question, right? You understood the concept. That's more important. Yes, I'm on I'm on Telegram. Yeah, DPPs. Yeah, we are posting out DPPs, right? We are posting out some DPPs. So now get into this question. Forget that question. That was a conceptual question. That was supposed to be a conceptual question, but anyway, there was 37.5 volts was supposed to be measured on that voltmeter. But you understood the concept. So a moving coil galvanometer of resistance, 100 ohm is used as an ammeter using a resistance of 0.1 ohm. The maximum deflection current in the galvanometer is 100 microampere. Find the maximum current in the circuit so that the ammeter shows maximum deflection. So assume in the circuit there is only like one ammeter attached to a battery, nothing else. Okay. So a moving coil galvanometer of resistance 100 ohm, internal resistance or resistance of galvanometer is 100 ohms, and you need to convert this into an ammeter using 0.1 ohms, and initial maximum deflection current is 100 microamperes. Now how much is that maximum current that you can, okay, minimum current in the circuit, okay, whatever it is, fine, forget it, but the ammeter shows maximum deflection. So that the ammeter can show maximum deflection, what should be the current in the circuit? What should be the current in the circuit? What can be that maximum current in the circuit be? Come on students, what should be the maximum current in the circuit? What would you do? Something is not going to change. Yes, that's it. It's really that simple. Yes, that's correct. So you are going what? Same thing. G into G is internal resistance or resistance of galvanometer into Ig is equal to that shunt resistance current. Okay, shunt resistance current into like the resistance of shunt resistor. Okay, which is going to be G into Ig is 100 ohms into Ig. It's 100 microamperes. You need to find out the value of shunt current, that's it. And then you would add this microampere current. Don't go for finding out the I also you can do, I guess, I minus Ig. Yes, same thing we are doing over here. Okay, so shunt resistance is 0.1 ohms. This obviously is nothing but 10,000 to the power 10 to if you do this you'll get this answer, right? Is is going to be how much? Is, the shunt resistance current is going to be 1 divided, so it's 10 to the power minus 5, 10 to the power 5, 1 by, and that's going to be 10 to the power minus 1, okay, ampere. Yes, answer isn't present over here. What? Just a moment. So 100. What is wrong with this question? Answer isn't there. IIT JEE question. That should be the answer, right? Answer should be correct. So there should be 100 ohms of galvanometer resistance, 100 microamperes, 10 to the power minus 6 is equal to 0.1 ohms. Okay. Maybe I noted down the question wrong, or there isn't any answer. Into shunt current. Yes. Okay, answer is A. That is correct though, right? Yeah. 0.1 ampere. Okay, 0.1 ampere. That is going to be written as like 100 milliampere. Yeah. 100 milliampere, and then you are going to add it with 100 microampere. That is like, yeah, that is going to be just a units conversion thing. Yeah, 100.1 milliampere. Okay, yeah. A should be the answer. Amazing, students. Hi. So that's it for today. We'll explore the potentiometer in the coming class. So keep enjoying physics, keep enjoying electrical instrumentation. This was a very easy question, and you saw how easy it is in electrical instrumentation. So do not miss any classes on electrical instrumentation. Hi everyone, and guys, do take care of your health, and do remember to share this channel with your friends. It's very important that you share this channel with your friends, and we will be able to provide education to so many people. Share it on your social media, on all the possible social media, Facebook, Twitter, anything that you have, like WhatsApp, etc. Do not forget to share the JEE English channel. And guys, gaining knowledge is also important, but it is also important that you share with your friends, you share with everyone that you know, so that you can amazingly develop your knowledge. You can help to the progress of humanity and evolution. And think about it, if you're sharing it, you are doing a nice cause, because someone who wants to prepare for JEE and do not have access, maybe in a village or due to economical conditions, this would be an awesome channel for them, especially if they are not very comfortable with Hindi or something. So do share this channel with your friends, and do not forget that, sir, can current go through shunt without having full deflection through? Yeah, it's possible, right? It can go through shunt without having full deflection. Yeah, full deflection means we taught in the beginning. Maybe you want to go back to the lecture, Suraj, and watch it again. What is full deflection and all has been told. So do not forget to share this channel. Keep gaining knowledge, keep learning, students, and also share it. Helps everyone who's in need of this, such high quality lectures for JEE preparation or for learning science and everything. And guys, do not forget to get onto a Telegram channel. This is available in the description box. Do click on that link, and you want to download the Telegram app and type in this link, or even on your browser would work. And guys, that would be amazing if you can get on our channel. You get all the live updates on special classes, on everything, like special classes, special Fridays, YouTube Fridays, everything in one place. That is going to be this JEE_English, and any video books, any notes, any DPPs, etc. are posted on this Telegram app. And guys, do not forget to also get on to my Telegram channel, and I created this Telegram channel for you students, so you can get on to this, and we can discuss about physics, current, electricity, JEE preparation. And guys, you can type in this link, https://t.me Murali_Unacad. Yes guys, yes. And students, this Friday and Sunday we are going to cover A to Z of current and electricity from 4 to 7 p.m. It's on Friday and Sunday. Do not forget to get to this channel, to this class on Unacademy Learning app, because even if you are completed, it's going to be new revision, new model problems. So keep enjoying. Come on this Friday, to this special class. It's going to be awesome. And how to attend this special class? You want to get onto this Unacademy Learning app. If you don't have one, install it. Go to your Play Store and App Store and install Unacademy Learning app. We have many such amazing special classes on this Unacademy Learning app platform, and you will also get amazing updates on all our channel. So guys, do remember, also you can purchase our subscription. If you're preparing for IIT JEE, be sure to choose your IIT JEE as your goal. I understand that you get all the lectures online over here and on special classes, but what about your test preparation? When it comes to test preparation, it's not just about learning lectures. You can be good in concepts, but still you need to give this test continuously to improve your aptitude, your speed, basically speed, agility, everything. Not only that, you'll get access to our top-notch educators. Not only that, you'll also have live interaction and doubt session with them, and live quizzes, live test series, and you have a leaderboard, national level standing, everything. So do not forget to get the subscription. And guys, if you're 9th, 10th, 11th class, you want to go for the 24-month subscription because it's a 2-year long journey. So don't forget to do that. And students, apply. Do not forget to apply the Murali live coupon, Murali live coupon, to get a 10% discount even on this amazing price. It hardly costs 1,500 per month. It's a very economical package. And take care, stay safe, bye bye, and we'll see you in the next class with new lecture on current and electricity, and that too on electrical instrumentation. And guys, do not forget to attend the next class, because in the next class we are going to discuss also a very crucial concept of current and electricity, that is basically electrical instrumentation. If you have gone through this chapter, mostly you are going to understand the next chapter without any hassle. Okay, and the other thing you have to remember is R is equal to rho into L by A. So let's see you in the next class. Take care, stay safe, bye bye. Get onto the Telegram channel, get onto the YouTube, and click on that subscribe button, click on that bell notification. Keep sharing this channel with your friends and everyone that you know. Thank you, take care, stay safe, bye bye.